So let's discuss the birth of stars. Stars are born in the stellar nurseries, so a little bit of review here. The space between the stars is not empty, but it has a significant amount of gas and dust. This is where the stars are born, in these regions where there is a little more gas and dust than normal. New stars form at a rate of about 2 to 3 per year in the Milky Way galaxy, which is really a very slow rate when you consider that the galaxy has about 200 billion stars. And they have to form in the cold, dense clouds with Jeans instability, meaning the conditions are right to enable gravity to take effect and produce the collapse necessary to form new stars. The interstellar medium is 74% hydrogen, 25% helium, 1 to 2% heavier elements, heavier than helium. The densities of the clouds vary. Some are hot, some are cold. They're thin or dense. And really what is needed is the cold, dense clouds, which are the molecular clouds, 10 to 30 Kelvin, 300 molecules per cubic centimeter approximately, and as already mentioned, 10 to the 15 times thinner than air, a quadrillion times less density than the air we breathe. By far and away the most abundant molecule is hydrogen, and of course that's by far and away the most abundant element in the sun and the rest of the stars as well. So the dense molecular clouds we're talking about still typically need a little bit of help. Gravity is insufficient to overcome the internal pressures and turbulence that conspire to keep the cloud from collapsing. So it needs to achieve Jeans instability, and this is typically triggered by such processes as bright new energetic stars and cloud collisions, supernova explosions, spiral arm compression of the clouds in the arms of the galaxy. So in simple basic form, this shock wave from whatever source comes along, hits the cloud. As it passes through, notice the compression, the squeezing of the cloud essentially in this simplistic picture. And as it progresses, that shock wave progresses, it produces the instabilities needed, so the densities increase to the point where the stars actually coalesce and ignite nuclear fusion on the main sequence, and off they go. So here's an example of this process. In this particular case, it's the Rosette Nebula. You see that radiation pressure from bright, energetic stars is pushing the gas out, and some of that gas is clumping into Bach globules shown here, the dark nebula, and that's the interesting regions because that's the densest gas and dust. And new stars will form in those dense globules. Actually, it's typically a lot larger than it appears, and it's seldom that just 1 or 2 stars will form, but typically tens, hundreds, or even thousands of stars in these globules. Here's a picture of a globule, invisible, and obviously it is dark. But as we've seen already, we know that there is stuff behind there, and in fact it can be revealed in the infrared. So the next image is an infrared picture of the same region, and there we see a protostar. So there is a new star being formed in this Bach globule. Once a molecular cloud achieves Jeans instability, the cloud will collapse and start to form stars. Well, the next stage is to produce a protostar. And once a protostar is formed, it's evolving toward what's called a pre-main sequence star. So here we see maybe a few hundred protostars in Centaurus. They're not very visible. They're hidden by the surrounding gas and dust. But eventually, as they produce more heat as a result of the gravitational collapse and accretion of matter, frictional heating, then they will start to shine and produce radiation pressure that halts further accretion. It halts the further accumulation of gas and dust onto itself. And that's a very important stage in the process of becoming a star. When the accretion stops, it exposes the protostar so that you can actually see it. It's no longer enshrouded in the gas and dust so much. It's pushed that out of the way. So it is now a pre-main sequence star. So here we have a couple of pre-main sequence stars that we can image. And at this stage, because the gas and dust has been pushed away, gravity is working with what it has, the material that it has, and contraction is slowed down significantly. And this continues to progress until eventually the core of the star gets hot enough to ignite hydrogen fusion, and a new star is born. A little bit more information on the processes up to the pre-main sequence. So you start with this gas cloud, and it has generally a certain amount of overall rotation, a certain amount of angular momentum. And conservation of angular momentum requires that as that cloud contracts, just as a ice skater who brings her arms and legs in spins up, so the collapsing cloud spins up. So you end up with what's known as a protostellar disk, and that's imaged graphically here. And it kind of flattens out because of gravitational and centrifugal and centripetal interactions to produce a disk of swirling gas and dust, the protostellar disk. And keep in mind that the energy associated with this radiating core here at this point is from gravitational collapse, the energy from gravity, from gravitational potential energy to begin with. So these are the main pre-main sequence stars. They haven't yet fully formed into a star. Well, interestingly, as it spins up and you have a lot of charged particles swirling around, you produce huge magnetic fields. So the magnetic fields and this high rate of spin combine to produce often what we see is protostellar jets, these bipolar outflows of particles and radiation that are seen coming out of these fledgling stars. And some of these jets that are produced, they typically come from some of the cooler stars, and these are known as T-Tauri stars. T-Tauri. You know, in astronomy, we don't often get such awesome images of stellar processes going on, but here is one of a T-Tauri star. Very young star, surrounded by obviously a lot of gas and dust that can be seen. And it's a gas ejecting star of the cooler G, K, and M spectral class. So that's the T-Tauri stars are G, K, and M spectral class stars. And they can shed a lot of mass while in their pre-main sequence phase, which they are. And as they shed mass, that's also associated with a brightening and dimming of the stars. So the T-Tauris are also seen to be variable stars. They vary in their luminosity output. Let's now look graphically at the process of a protostar becoming a pre-main sequence star. And what you see here are various tracks. These tracks are the progression as depicted on the HR diagram of the various mass stars as they are approaching pre-main sequence and ultimately main sequence. So obviously there's a lot of differences in the various masses. Well, the blue birth line, this line along here, is the point at which the protostar becomes a pre-main sequence star, and the radiation pressure has cleared out the accreting matter, and it is continuing to evolve through gravitational forces and nuclear processes to become a main sequence star. So these dashed lines, as you see here, are actually corresponding to the stage on this diagram pertaining to the age shown. So as for instance, we see here at 10 to the 6 years, or a million years, that's just about the time where a 3 solar mass star is reaching the birth line. So that's how that works. And keep in mind that the birth line event itself is preceding the main sequence. So this is the stage just prior to the star becoming a main sequence star, which of course is the ultimate goal. So now let's track the star from the collapsing cloud all the way to the main sequence. We have the protostars shining by gravitational energy and ultimately fusing hydrogen at the main sequence. But it takes a star like our sun, which this example will depict, millions of years to get to that point, and the contraction slows down throughout the entire process, continuing to release, radiate energy away. As it radiates the energy away, gravity has the ability to continue to compress it down because the heat is being released, reducing the internal pressure. So this process continues on and on. The protostar reaches a temperature. This is kind of like off the HR diagram, but ultimately here it's getting onto the HR diagram. It's like an extrapolation of it. And you notice about 3,000 Kelvin or so, and about 10 to 100 times the luminosity of our star, the sun. So it's shrunk to the point of reaching that temperature. And at this point, really what we see right here is where the surface temperature rises to the point where radiation pressure is sufficient to clear away the surrounding region. This is the birth line. This is the point where the protostar becomes a pre-main sequence star. And now as it continues to compress, continues to contract much more slowly, it shrinks in size and the fusion rate rises. The fusion rate inside the star really triggers at about 10 million Kelvin. And when that fusion rate inside this pre-main sequence star balances the energy radiated, that fusion energy is balancing the gravitational contraction, and it achieves hydrostatic equilibrium, you are now a main sequence star. That is the condition where it stabilizes out at that point. How about some examples of where all this is happening? Well, here is a famous nebula, the Eagle Nebula. And wonderful stellar nursery, very beautiful. Here's the eagle. Notice the head, the upper beak, the lower beak. I guess perhaps this is one wing and maybe the other wing here. But in any case, you kind of see the eagle's head. So the Eagle Nebula is a region where bright stars are carving out the gas and dust, producing these various plumes that are perhaps almost looks a little Halloweenish, a little ominous. It's an ionized hydrogen region, again, meaning that the hydrogen gas has been stripped of its electron, so it's protons and electrons. And photons from an O-class star can literally ionize this hydrogen from 30 light years away, so the ultraviolet photons are very powerful. And they are all quite close together, so it's not long before the electrons will be recaptured by the protons and there'll be a cascade of the electrons going down to the ground state or other energy transitions and produces the red hydrogen alpha emission that you generally see in these emission nebula. And again, the intense radiation from those stars and other nearby stars cause the carving out of all these various pillars and plumes that you see. Well, let's look at this beak region in a little more detail. This is an incredibly detailed, high-resolution image of a actually quite vast region of gas and dust. And what you notice, if you look closely, don't know how much detail you can see, but the image reveals a whole bunch of areas where the fledgling stars are being revealed as the radiation pressure carves out the surrounding gas and dust. So kind of like when a wind is blowing real hard and you want to get away from it, you hide behind a truck or a house or some other person and you are blocked from the wind. In like manner, you see these pillars where the star is revealed and it's shielding the gas and dust behind, so they look like little stringers coming off of there. So those are newly forming stars in the Eagle Nebula. Very, very awesome process showing this all taking place here. Sharpless 171, 20 light years wide, a nebula in Cephas. You can almost visualize the radiation pressure carving out these various huge plumes of dust and gas. And here again is an example of a stellar nursery in the process of producing new stars. Back to the Orion Nebula, we have a process taking place that's very important in the development of stars in galaxies, and they're called OB associations. They're bright OB stars, typically in clusters. Well, in the Orion Nebula, we have an example of that. It's called the trapezium stars. There's 4 bright young stars, less than 2 million years old, in the central region. And they have the ability to actually ionize the nebula, which is why you're seeing the hydrogen alpha emission, Balmer lines, Balmer emission. And in much more detailed view, here we see those 4 stars. And what you notice also here is the fact that they're producing cavities in their vicinity and shock waves. So here's some shock waves. Notice that they are shocking the surrounding interstellar medium. And of course, we've already seen that those shock waves can be the impetus to produce the gene's instability in subsequent molecular cloud regions. So in this way, the OB associations, these stars, these bright energetic stars, can produce a chain reaction of new star formation deep into the molecular clouds. So let's look at that in just a little bit more detail. So how does the OB star progression into the molecular cloud take place? Well, it's really pretty simple. So here we have that bright OB cluster, like the trapezium. And they're energetic enough that they act as the radiation pressure acts as a shock wave, impacting the molecular cloud, shocking new stars into existence and to be informed, while there's a region of ionizing radiation here. And so in this way, new stars are being formed, and as those new stars come into existence, some of them are very bright and energetic, so here they are. Here's the old cluster. So you see how we progressed into the cloud already. Then the original cluster is dispersing, while the new cloud, the new stars, is producing shock waves into the cloud, triggering new star formation yet deeper. And then in the final image, we see the sequence once again, the older cluster, the oldest cluster, and here's the new cluster that is once again producing its own shock waves, triggering more star formation. Now this has actually been imaged. Here's an example of a star that is produced through its shock waves, new stars in its wake. This is a very important and fundamental way in which stars are produced in the galaxy.